Okay, so yeah, this is the very tail end of 2.3. And we talked about what in most of 2.3? Mean, median, and mode. And because those are measures of central tendency. What this is describing the shape of a distribution. You know, what we've done in chapter 2 is collect the data, and in 2.1, remember we made frequency distributions, and that meant to visually show the information. It looked like a histogram where we had the bars. And that's what this looks like, is a graph that has all of these bars. Now, here's what's true if a distribution is symmetric. You will have a line, a vertical line that would go right through the center of your data, and you would have a mirror image on the left side and the right side. Most of the time, if it's symmetric, it looks like this, that you have most things in the middle, and then the side to the left will probably be going down. The side to the right of that will probably be going down. And usually, we talk about this as, we could describe it as a bell-shaped curve. Does that sound familiar? That's the idea, that most things should cluster in the center, and then you don't have as many out on the ends. Now, if it's completely symmetric, your mean, your median, and your mode will all be the same value. That's kind of cool. All right, that's if it's completely symmetric. Now, let me just point something out. What if, let's say this bar right here had actually been a little bit taller, and this one had been just a little bit shorter, but everything else was pretty much lined up? Would it still be symmetric?
No.
Actually, we would say yes, it's basically symmetric, it's just not completely symmetric, okay? But if the general shape looks like the center is where most everything is gathered, and it slopes down from there, then we would still say it's basically symmetric, as opposed to some other things that I'll show you in a minute. Now, this is also symmetric, but what do you notice about these bars? They're all the same height. So this would be if you collected data, and let's say, you know, you were asking some question about maybe what's your favorite number? I don't know, something very random. But let's just say somehow we got 20 who said 1, 20 who got 3, 20 who said 5, and so forth. And every one of these numbers had exactly the same frequency. You get what's called a uniform distribution. There's no variation in it at all. It looks like a big rectangle because you have equal frequencies. And notice it says that you have equal or approximately equal frequencies. That means if you're looking closely, this bar and this bar look like it might be just a hair short of 20, might be more like 19 on the responses there. But if it's exactly uniform, look at this, your mean and your median will be the same. Why is mode not up here? Because they're all the same, okay? So you don't see these often. It's a uniform distribution. Now, this is where you got to make sure this part makes sense. We have our high point clustered here, and if I look on either side of the high point, would you say it looks like one tail is longer than the other?
Yes.
Yes, and so that's the way I would look at it to decide whether something is skewed left or skewed right. Which side has the longer tail on this one?
Yeah.
On the left side. I just go a little bit to the right of the middle and I'm done on the right side. But if I go to the left, this is a much longer tail. So we say it is skewed left. We have more data on the left of the center of the highest frequency than we do on the right. And notice what that shows us. If we were to calculate the mean, it's going to be to the left of the median. All right. My value that would be, excuse me, for my middle point, my mean, because I have more values that are smaller on the left side, is going to pull my mean down, and it will be smaller than the median. So does it make sense if the tail's longer on the right side, you'd say it's skewed right? Yes or no? Does it make sense if I look at this, and this is the tall part, that I have a longer tail on the right, so this thing is skewed right? What's that going to cause the mean to do? Will it be smaller or larger than the median? It'll be larger because I had more data to the right, okay? And that's everything on those distribution shapes. We will be talking about those more later, but right now, let's talk about section 2.4. So everybody got your notes, right? And we've done range before. How do you find the range of something? You take the largest number, subtract the smallest. It's always the difference between the maximum and the minimum entries in your data set. That would mean my data must be quantitative, right? Otherwise, how would you answer something like, how much is red minus yellow? Makes no sense, okay? So your range has that little formula. By the way, you know the little formula sheet that I gave you? Make sure you know how to read this, because, and I'm going to go over this with you again in a little bit, but the formula for finding the range is actually on here. If you look down about, I don't know, 8 or 9 on the left side of your sheet, you see range equals maximum entry minus minimum. You do get to use this when you test. Okay, so hang on to this thing. Now, let me tell you one more thing about it. As long as you have not written on your copy, you get to use it on the test. Like if it's sort of makes me feel comfortable because it smells like mom. I sprayed it with her perfume and it makes me relaxed and happy. So if I can test with this, I will have less stress in my life. That's fine, as long as you haven't written on it. But if you do write on it, then you will have to use a clean copy that I provide you when you test. Now, having said that, here's my suggestion. You know, we started learning those Greek letters last class. We talked about those. If you need to put some extra notes on here to remind you, oh, this symbol means add everything up, or this is the one that stands for population mean, that's fine. Write it on there. Just understand you can't use that one when you test, okay? All right, so I've covered that with you. So let's see if we look at this list. Can we find the range? You got a corporation, they hired 10 graduates, and here are the starting salaries shown in thousands of dollars. We talked about this last time as well on that stem and leaf plot, how sometimes you may need to show somebody the key that goes with this, because if we did a stem and leaf plot of this, when somebody sees 41, they need to understand, no, that's $41,000. Okay, that's what that means. Now, find the range for me. So what would we need to pick out of the list?
Smallest.
Say it again?
The smallest and the largest.
Exactly. Y'all agree with him, right? Smallest number and the largest. What's the smallest? Looks like 37. I would hate to be the one that got hired at that salary if everybody else got more. Which one got the most? What number?
47.
Looks like 47. So what would you say is the range of the starting salaries? $10,000. Very good. So we take 47 minus 37, and the range is $10,000. Now, logically, if I were just to ask you, would there be some good reasons why you might have that much difference in starting salaries if everybody just graduated college? What could make a difference? Could be the position, might be the level of training, you know? I mean, maybe you're all getting hired as some kind of engineer, but maybe somebody's already gotten past some sort of certification test, so they're qualified to do more. So there's some different reasons why they might be different starting salaries. Now, we need to have tools that let us recognize important differences, all right? One of those is calculating a deviation, the difference between the data entry and the mean of the data set. Now, we found the range a minute ago. Do you think we could find the mean?
Yes.
We could, and we're going to do that in a minute. So once I know what the mean is, To get the deviation for each of those entries, I have to take what the entry is and subtract the mean from it. Now think about that for a minute. If my low was 37,000, my high was 47,000, shouldn't my mean be somewhere in between there? So when I add up all those numbers and I divide by, I think there were 10 in the list, I'm going to get an average or a mean starting salary that's probably going to be, I don't know, 41 or something thousand. So if I'm using this formula and I'm the guy who got hired at 37,000, what kind of number do I get when I do 37 minus 41?
Negative.
Negative. So that means when I'm calculating deviations, I'm going to have some numbers that are positive, some numbers that are negative. Is it possible I could even get 0?
Yes.
Yeah, because it might be that the individual salary in the list, maybe my salary, is exactly the same as the mean. Okay, so if I'm working with a sample, remember, instead of this Greek letter that we see up here, which goes with population. Do anybody remember the name of that? This is what letter?
Mu.
Mu. Mu. Yes, the Greek letter lowercase mu for population, because we always use Greek symbols when we're working with a population. When it becomes the sample, instead of mu, we use what to represent the mean? What do we call this one?
X bar.
X bar. Very good. Okay, so we're back to the list of salaries. In order to find the deviation, you're going to have to find what? The mean. So I want you guys to find the mean. That means you're going to need a calculator, and you're going to come up with what the average salary is. To our PowerPoint. Let me make sure we're recording. Yes. And we found our mean. We built our table where we took each X value, subtracted the mean, and we found that when we added all those up, we actually got 0 because some numbers were positive and some were negative. We're going to come back and talk more about this in a minute, okay? Because it's only part of what we're going to need in order to find the other things that are going to be helpful. So we talked about the deviation. Here's the next formula. It's the variance. And just like when we looked at the formula for mean, even though you find it the same way, we had a different notation we used when it's a population versus a sample. So here's our formula for population variance. You have a new Greek letter that has appeared, okay? A few years back, some of your former classmates called this turbo. Do you know why? I think it had something to do with cars, Disney cars or something. I don't know. Anyway. Oh, it looks like the snail. Is that what it is? Okay. Well, what that is a lowercase sigma in the Greek alphabet. You remember the big kind of E-looking thing was the capital sigma. This is lowercase sigma. And sigma squared is our population variance. Look at the top part of this formula. Does this part look familiar without the square on it? What is that? Did we just find it? What was it called? Do you remember? The deviation, exactly. And the problem was, if I just add up all the deviations, it always gives me 0. So this is telling me, find all of the deviations and square them. Then add them up. What happens if I square a negative number? Becomes a positive. So that's going to keep me from getting 0. This is called the sum of the squares. The population variance, the numerator is the sum of the squares. And then we divide it by how many things we had in our list. So let me show you this. And here's what I want you to see. Okay? The variance is what we just found. That was the sigma squared, right? The population standard deviation, now this is different from deviation. Remember, the first column that we did was just getting the deviation. How different is the number in the list from the mean? And some were bigger than the mean and some were smaller. That's why some were positive and some were negative. Using this formula lets us come up with a method, a tool, that will let us explain what would be more or less what you would expect the average difference to be. How much variation is there in salaries? Okay, I can't add the deviations because if I do that, I just get 0. But this gives me a tool that'll let me say about how different could somebody's salary be from the mean. And so a standard deviation is very useful, and you're going to find that it comes up a lot. If I've gotten the variance, look at this formula. It doesn't have a square on it. So what am I going to do? How do you get rid of the square from the formula I used? Take the square root. So I'm going to find the variance and take the square root of it, and that's going to give me my standard deviation. So here are your symbols. You got your mean that we found first. Then we got the deviation by subtracting the mean from each of the values in the list. Then we squared each one of those, added them up, and divided by the number of items that we had in the list to start with. To get the standard deviation, take the square root. They've written it out for you with 6 steps, okay? So if we were to do that with this problem, you guys already told me the sum of squares added up to be 88.5. We calculated the variance and we got 8.85. They rounded it to about 8.9. It's up to you. It kind of depends on if you've been given some instructions on how to round. Now, the standard deviation will be the square root of that number. So if we take the square root of that, it's going to be 2.97 or something like that. They've rounded it to be about 3. So you would know that the population standard deviation is about $3,000. So if my mean is 41,500, it's telling me most of the salaries will be within $3,000 below or $3,000 above. Now, when I say most, we're going to be looking at some percentages that will give you an idea of what most means, okay? Because we'll talk about if it's within one standard deviation, what you would expect to be in there. But this is the formula for how you calculate it, okay? If it's a sample, remember our symbols change. And there is a difference in the formula that you use for variance in a sample than a population. Do you see what it is? Yeah, my denominator is different. Okay, I mean, I still take the x minus my mean and square it and add those up in the numerator, but notice the denominator says n minus 1. Now, think about it for a minute. If I have a sample, is it possible that the information from the sample could be pretty different from the population? I mean, I can do my best to try to get a good sample, but is there always the possibility my sample might not be as representative as I would like it to be? Could be. So this has been, over time, it's been refined, and to kind of reduce the amount of change that you could have because you've got a sample instead of a population, that's what they have done, is reduce the denominator by 1. And that kind of tweaks it just a little bit to take into account that your sample might be off a hair, okay? And then you still just take the square root of that to get your sample standard deviation. So instead of the lowercase sigma, we just use a lowercase s when we need a standard deviation. Here's the same thing going through the formulas. All of these formulas are on that sheet I gave you. Do you see them? They're listed for you for both a population and for a sample. So let's see if we could find this. This is the same information as we had just a minute ago, except notice what changed in the instructions up here. This is for the Chicago branch of a corporation. There are other branches, so you're going to use the starting salaries of the Chicago branch to estimate the starting salaries for the larger population. Find the, what word is italicized?
Sample.
Sample standard deviation of the starting salaries. So if we're going to get the standard deviation, but now this is a sample, not a population, do we have to go through the whole table again, or do we just have to make a little adjustment?
A little adjustment.
And what's the little adjustment? Instead of doing 88.5 divided by 10, we'll do what? We'll divide it by 9, because 10 minus 1 is 9. Now, let me show you this. Okay, we still have the 88.5, but they're dividing it by 10 minus 1. And then remember, they kind of rounded on the other one to the nearest tenth instead of keeping the extra digit. And so this is about 9.8. Now, if I take the square root of 9.8, what does that give me? 3.1. So instead of saying that the standard deviation is 3,000, which is what we had if this is the population, now the standard deviation of the sample is 3,100. It's a little bit bigger. Here's what I meant when I said the sample could be skewed a little bit. So to try to make sure that we would have, when we start talking about how many standard deviations from the mean, that we end up with the right percentages, we're going to have to make the standard deviation just a little bit bigger on a sample, because we may be off a little bit. So that means if we make it a little bit bigger, we're going to get more data in there to kind of help balance out for the fact that I don't know what the whole population is. I'm just working with a sample. Okay? Does that sort of make sense? Now, here's the part you guys are going to like. You want to see how to do this in the calculator?
Yes.
Aha. Okay. So what you would need to do, just a moment, I've got to get back where you can see the screen. Okay, so what you would need to do is take all 24 of these numbers, and you want to enter them into your list function in the calculator. So you press Stat, and you hit Enter to go into Edit, and you're going to type all 24 of these in L1. Even though it's 3 columns here, they're going to go into 1 column in the calculator. After it's there, in order to see in the TI 83 or 84 this information, what you have to do is press Stat again after all the numbers have been entered, and then you arrow right to Calc, and you choose number 1, which is 1 variable stats, and tell the calculator you want it to use the numbers in L1. And this is what you'll see. Remember, X bar stands for mean. And it doesn't matter if it's a sample or a population, you find the mean the same way. And then because we were working with a sample, that's why the S of X is circled here, because this is the sample standard deviation. If we'd been working with a population, then the line under it that says sigma X, that's going to be the population standard deviation is what we would use. It will not give you the variance here, but remember, you find the variance if you take the standard deviation and you square it. So here's what you find when you are using a standard deviation. It just gives you a better feel for how different are most entries from the mean. So if you look at these 3 graphs, here's what you would see. On the first one, the average is 5 because all 8 people had an answer of 5. I'm not sure what was being measured, but the mean is actually the same thing as all the responses. There is no variation whatsoever in responses from the mean. So that would mean your standard deviation is 0. Everybody's is the same as the mean. Now, if you look at this one, this is a symmetric distribution, and if you calculate the mean is still 5, but not everybody had 5 as their response. And so if I use my formula to calculate standard deviation, then I get about 1.2, and it would mean most of my data would be within 1.2, either above or below 5. So it would go up to 6.2. It could go down to 3.8. Look at this last one, though. My mean is still 5, but I have absolutely nobody in the data list that has a response of 5. And look what's happened to my standard deviation. It's gone up to 3, and that's because most of the data is very different from the mean. So that's what a standard deviation will help you do, is see how different most of the data is from the mean. The more your entries are spread out, the larger your standard deviation will be. Now, here's those percentages I've mentioned that will help us interpret this. As long as we have a symmetric or a bell-shaped distribution, these are the characteristics that you will have. About 68% of the data will be within 1 standard deviation of the mean. Okay, so if I know the mean, 1 standard deviation above and 1 standard deviation below, if I were to block that off, I would have 68% of the data there. If I go 2 standard deviations below and 2 above, I'm going to have 95% of the data. If I go out 3, I've got 99.7% of the data. So that's practically everything. That means there's just a little tiny room for a few things to be further away than 3 standard deviations. But this is called the empirical rule. As long as it's a symmetric or bell-shaped curve, these percentages should hold, okay? So 68% within 1 standard deviation. When you go out 2, you get 95%. 3 standard deviations from the mean will give you 99.7% of the data. So here's an example. You've got a survey that has the sample mean height of women in the U.S. It's 64.3 inches for women aged 20 to 29. The sample standard deviation is 2.62 inches. Could we estimate the percent of the women whose heights are between 59.06 inches and 64.3 inches? Well, in order to do that, we're going to have to figure out 59.06 is definitely below the standard deviation. So we're going to, it's definitely below the mean. So we're going to have to figure out how much below the mean it is. And then we would need to recognize that our second value they gave us actually is the mean. So we want to figure out how many standard deviations below the mean this will be. And here's what we would see. We're going to have that 59.06. If I were to, let's go back one and look at this. Since my standard deviation is 2.62 inches, if I take my 64.3 and I subtract 2.62, I am not yet at 59.06, which means 1 standard deviation below didn't get there. But if I subtract 2.62 again, I do end up at 59.06. So here's my mean. 1 standard deviation below was my 64.3 minus the standard deviation. I have to subtract off 1 more standard deviation to get here. Now, that is not also including what's 2 standard deviations above. I just want to know from 2 standard deviations below up to the mean. So there's a couple of ways you can figure it. They are showing you if you divide up all these sections, you can just add up the 2 sections you need. The other thing you could do is I want the half that's below the mean that's 2 standard deviations away. Well, I know if I had the half that's above the mean, then from here to here would be 95%, and half of 95% is 47.5%. Okay, so you've got more than one way you can figure it out. Last thing to talk about in this section is Chebyshev's theorem. And the difference between the empirical rule and Chebyshev's theorem is this. Chebyshev's theorem applies for any kind of distribution. It doesn't have to be symmetric or bell-shaped. The empirical rule only works for bell-shaped or symmetric distributions. So if I don't know if it's symmetric, I can still figure out about how much data should be within 1 or 2 or 3 standard deviations if I know Chebyshev's theorem. And here's the way it works. K represents how many standard deviations away from the mean. And so my K has to be a number larger than 2. I really can't figure out what percent of the data would be within 1 standard deviation, but I can come up with some values for data within 2 standard deviations of the mean. And I do it this way. I would do 1 minus 1 over K squared. So if K is 2, then we would be calculating the percent of data that's within 2 standard deviations of the mean. So if I put in 2 for K, 2 squared is 4. 1 minus 1/4 is 3/4, which is 75%. So it's not as high. It's not, I can be more confident how much would be within 2 standard deviations of the mean when I know it's symmetric or bell-shaped. If I don't know the shape, I've got to lower that percentage, and that's what Chebyshev's theorem will do for us. So 75% would be within 2 standard deviations of the mean.